In this lecture, we are going to study about the concept of electrostatic field. So if you remember, in the last lecture, we discussed about electrostatic force, that is Coulomb's force. So when you have two charges and both the charges are at a distance, suppose r, so there exists a force. So if the charges are similar, it's going to repel. If the charges are dissimilar, positive and negative, there is an attractive force. And the force at a distance, that is action at a distance, we call that is due to electrostatic force. And we had an expression, if you remember, the magnitude of that force, it was given by Coulomb, and it was 1 over 4 pi epsilon naught. If Q1 and Q2 are charges, then it's product of charges divided by square of the distance between those charges. Now the question comes that if this action is happening and this action is happening at a distance, then how do we conceptualize that how this push and pull is happening? If there is a similar charge, there is repulsion at a distance. If there are two charges which are dissimilar, there is an attraction at a distance. So how to conceptualize this? Michael Faraday came up with a concept, and he imagined the area around a charge. So charge at rest, he imagined and visualized that there is lines of force that exist, or rather, in other words, we can say there is an area of influence. So to test an area of influence, if you keep a test charge, and if it gets a force, if it experiences a force, then we say that the area of influence exists there. And he imagined lines of forces emanating from the charge. Say, for example, if you look into this diagram, suppose if we have a positively charged glass rod, and we want to find in this area, we bring a test charge. And what is this test charge? A test charge is of very small magnitude. So the influence of this test charge in terms of its contribution to the lines of force that he conceptualized, that is negligible. And if we consider this at a distance, and this test charge is experiencing a force F. So this is positively charged rod, it's going to experience the repulsive force. If that is so, we'll say that this is the area of influence of this glass rod, positively charged glass rod. So from this concept of lines of force, a concept of field came into picture. So it is like these lines of force if it is imagined. Although in reality we don't attach much, the scientific community don't attach much importance to these lines of force. However, quantitatively it may not be relevant, but to visualize the pattern, it gives an idea how the area of influence is spread across. And this non-contact force, which is force at a distance, action happening at a distance, could be explained in that sense. So suppose you have now a negatively charged body, and this negatively charged body, if you want to test the area of influence, we have a test charge again Q naught here. And if this Q naught is getting attracted towards this, so with this one it's going to get attracted, and we'll say then this is the area of influence exists there, and we'll say the electric field exists there. So this electrostatic field that we are talking about, E field, it is the notation is E field. This has a relation. So this electrostatic field E is actually this force which is experienced by the test charge per unit test charge. So if we know this expression, that electrostatic field that we are talking about, in terms of its magnitude, is defined as this electrostatic field is electrostatic force per unit test charge, the charge that we have placed to test what is the force being experienced, and the direction of this electrostatic field. So this field is a vector quantity. Electrostatic field is a vector quantity. The direction of this electrostatic field is same as electrostatic force, and then we have this relation to explain this quantitatively that this is the relation that we have with the field and the force that we are discussing today. So let's again visualize few patterns here. So suppose if you take a positive charge here and it is placed in space, so it has a spherical symmetry if you look at it. So if you imagine the lines of force or the electric field lines that we call these lines as electric field lines. So these are electric field lines. These field lines are radially outward. These are radially outward. If why? Because this is the positive charge. So if you look into this diagram, we have a negative charge here. So obviously the field line's direction will be opposite. It would be radially inward. This radially inward is giving you this spherical symmetry, right? In your imagination, you would imagine a spherical symmetry. In a space, this negative charge is kept and you have these inward field lines coming into it. So if we go step by step and figure out these field lines, what is the pattern that we get? What is the pattern when you get two similar charge of equal magnitude if it is placed in close proximity and you have the nature is same, then what is the pattern that we get? So with all these we'll be going through this, but let's move on to some important points. These are those properties of electrostatic field, which is a vector field that we are talking here about. So the first thing that we are going to understand is these lines that we see, this could be curve, this could be straight line, it depends. So if it is a curve, the straight line is going to give the direction. That is straight line, we already know that it's the same direction as that of force and it's a central force. So if it is straight line, it's going to give that direction. However, if you have a curve there, so the tangent to a line at any point gives the direction of the electric field at that point. So if you draw the tangent to this curve, it's going to give you the direction of the electrostatic field. Why the curve is there, we are going to then understand this curve is there because if we consider the charges, suppose one is positive and one is negative, right? So from positive it animates, it comes out, right? It comes out and then it starts from positive, terminates in the negative. So it begins in the positive charge and terminates on the negative charge. We can have this as a second property of electrostatic field. The third property says the number of lines leaving a positive charge or entering a negative charge is proportional to the magnitude of the electric field, right? So what does it mean? It means that if you have this charge, if you look carefully, it's quite dense, right? Why it is dense? Because the number of lines which are coming out, per unit area, if you are going to figure it out, it's going to be more lines are per unit area, right? And this is perpendicular to the plane. So the number of lines actually leaving this positive charge and entering this is proportional to the electric field. So when we draw the pattern, we need to keep that in mind. And as it moves further away, the electric field strength decreases. Why? Because we have that relation, right? We'll come on to that relation again. But in the diagram, we see a dense here near to the positive charge. Why? Because the strength is more. And as we move away, it goes further apart. So that is what it says, the third property. The number of lines of force leaving a positive charge or entering a negative charge is proportional to the magnitude of electrostatic field. The fourth point could be very important. These lines that we have made, these do not intersect anytime. So no two lines of force, magnetic field lines, they cannot intersect. If they intersect, then at that point, which is the intersection point, there would be two tangents, which is not possible. Why? Because the tangent shows the direction, and the direction could be just one. It could not be two directions. So two lines of force cannot intersect. Fifth point, the electric field lines starts normally from the surface. So where it starts, you just ensure that this plane, and it starts normally perpendicular to that plane of the surface, right? And the 6th point says, very important, electric field lines are drawn from higher potential to lower potential. So as we move on, we'll be studying about electrostatic potential. So you will be knowing about electrostatic potential, equipotential surface. So those terms and terminologies will be studying later on. But at this point, we need to remember that it comes out of the higher potential and terminates at the lower potential. So if you look at this pattern, let us see if it comes with those properties. So we have two equal charges, positive and positive, and the nature is positive, the magnitude is same, and we see that this repulsion is happening. So these goes, why? Because positive, positive, positive repel, and we see these two lines are repelling, and there we have sort of null point, and this is showing you the resultant pattern when you bring two similar charges equal in magnitude. Suppose we take an example of this one. Now this is a supposedly infinitely large non-conducting sheet, right, and which is positively charged. Although it cannot be in real sense infinitely, but if it is very large, we can assume that. So what kind of electric field lines we'll be getting? You would look at it in this way, that this is the plane, right, and we are going to follow the properties. So if you are going to draw the electric field lines, it's going to be straight and equally spaced. So the electric field that comes out of it is actually uniform electric field. And how are we depicting that in the picture? It is, these are the lines which are coming straight, and these are equally spaced. So these are parallel lines, these are equally spaced. These lines shows that there is uniform electric field that exists. And suppose here you have a test charge here. It's going to experience a force in the same direction of force, and it's going to be the same parallel direction, right? So this is what gives an idea of how can we have a pattern for uniform electric field. Now in this diagram, if you look carefully, this has one positive, this has one negative, and relatively we have small distance. So this kind of combination that we have is famously known as dipole. Dipole means two poles of opposite nature of equal magnitude. So if you draw the field lines, electric field lines pattern, we see that it starts from the positive, terminates at the negative terminal. We need to remember it does not form a loop. It starts and terminates. And if you look carefully, at the start point here, it's dense. The electric field lines are dense. At the terminating point, it is dense. However, as it moves further away, it is spaced, and right? So these are like sort of non-uniformities there, and these are curves there, not equally spaced, but the space varies. Why? Because it is proportional to the electric field lines will be proportional to the magnitude of the charges, and we see as we move further away, it is inversely proportional to the square of the distance between them. We'll look into that equation later on. So if you look at here in this area, it's going to be coming out from the positive charge, and here these electric field lines are entering into negative charge. So here we have drawn a tangent to show that this is the direction of electric field from positive to negative. So for a dipole, we do have this pattern for electrostatic field. Please note it down. It's quite important to have this information about electric field. So if you have any questions regarding this, certainly you can put those questions in your comment box and try to understand this, visualize this, and it's quite interesting to know more about it. As we move ahead to the further, we'll have more derivations there of different charged bodies, and we'll be deriving an equation for electrostatic field, resultant electrostatic field. So let us check here what is going to be the value of it. So if suppose you have a point charge here, I'm rubbing this. If you have a point charge here and you want to find what is the magnitude of this using the equation that electric field is defined as, this electric field is defined as, I'm writing it in this way, electric field is defined as this force over Q naught, where Q naught is the test charge. And suppose you have two bodies, 2 point charges, and we have Q and Q naught. Q and Q naught are, Q is point charge and Q naught is test charge. So what is the magnitude of this electric field? It would be 1 over 4 pi epsilon naught Q naught, right? So this is force Q naught and divided by R square. But we need to divide this by Q naught again, right? And if you want to vectorially represent this, suppose we have R direction, so I'm representing the unit vector R as a direction, and this is going to cancel Q naught, so therefore vectorially we will have this equation as electric field because of the point charge Q, having a charge Q, is 1 over 4 pi epsilon naught Q divided by R square unit vector R. So this is the equation we have derived for point charge. The resultant electric field because of a point charge is coming out to be 1 over 4 pi epsilon naught Q by R square. So what's going to be the unit? Here it's going to be the Newton, and here is going to be in the denominator it's going to be Coulomb, right? So the force over charge is the value of this electric field. So these are few important concepts related to electric field. In the next chapter, in the next lecture, we are going to study more about the derivation part. We have different charge bodies and the resultant electric field could be calculated. So make sure you watch the next lecture. Thank you.